por este medio le reitero mi agradecimiento al doctor Michel Virlogeux de haber aceptado venir a nuestro seminario. Actualmente, bueno, desde hace 30 años se vive una revolución en el dominio de los puentes. Los claros se han incrementado, se han roto récords del mundo constantemente en cuanto a longitud y complejidad de los puentes. Michel Virlogeux es uno de los principales participantes de esa revolución, es uno de los grandes diseñadores de puentes actuales y de la historia. De hecho, voy a leer su semblanza. Michel Virlogeux es egresado de la Escuela Politécnica de Francia en 1967. Igualmente se graduó como ingeniero de caminos y puentes en Francia en 1970. Es doctor en ingeniería de la Universidad Pierre y Marie Curie de París. El ingeniero Virlogeux, el doctor Virlogeux, comenzó a trabajar en el CETRA, que es el equivalente de la SCT francesa, en 1974, y trabajó de ahí de 1974 a 94. A partir de 1980 fue jefe de la división de grandes obras de concreto, y entre sus grandes realizaciones está, por mencionar algunas, el puente de Normandía, que en su época fue récord del mundo en cuanto a claro, duplicó el claro que existía precedentemente. El puente de Millau, que todos lo conocen, es un puente muy hermoso que está en Francia, y es otro puente. También el ingeniero Virlogeux, entre otros méritos, que ha recibido muchos premios a lo largo de su carrera, es caballero de la Orden del Mérito de Francia y es caballero de la Legión de Honor de Francia, el grado que obtuvo en 2005, que es el más grande mérito que otorga la República Francesa. Bueno, ya no le quito tiempo, queremos escuchar con ansias al doctor Virlogeux. Adelante, Michel.
Thank you very much, Alberto. This is a great pleasure to be once more in Mexico. I've been several times before, but long ago. I think I've not been in Mexico since about 15 years. Today, I shall give a presentation of a big project which is just very close to completion. It will be probably finished and open to traffic in July or August. It is in Turkey. You see, Turkey is crossing in the same time in Europe and in Asia, which is, these two parts of Turkey are separated by the Marmara Sea, which is a very important international maritime route, passing through the Dardanelles crossings from the Aegean and Mediterranean Sea to the Marmara Sea, and with the Bósforo Straits between the Marmara Sea and the Black Sea. Of course, this crossing, this Bósforo had to be crossed. It is already crossed by two bridges, one which was built in 1970 by Freeman Fox. This is the second bridge of this type with a very streamlined box girder. And the second one was built about 10 years later by almost the same team and by a Japanese company, Ayachai. In fact, the new bridge will be in the north of the Marmara Sea, very close to the Black Sea, and because Turkey wants to develop this northern eastern part of the European part of Turkey, because the Istanbul area is completely congested. Of course, one of the big problems is that the Bosphorus is a very important maritime route, such important with some risks in navigation that the cargo ships can pass only in one direction at a time, during 12 hours in one direction and then later in the other one, like in the Panama Canal. In fact, in the Turkish government plan, the bridge has to carry a motorway with 4 lanes in each direction and 2 railway tracks. This is very much. In addition, it was supposed to be a suspension bridge to the span, and there were 2 little sentences in the competition documents. One for the bridge architectural quality, 2 for a similitude of shapes with the 2 existing bridges. And this is very important because if you look to the shape of classical suspension bridges with roadways and railways in the same time. This is classically a truss with two levels and with the railway line at the bottom level. This leads to very huge structures, 12 to 14 meter high, which are very heavy and which, in my opinion, can by no way be an elegant bridge. But the problem is as follows. If we design a bridge with a streamlined box girder, and if we place a train at about quarter span, there is a huge deflection downwards. Why? It's because the suspension cables go downwards in half the span and upwards in the other part. That means that the main suspension cable tries to escape from the load. And so this is leading to a very huge vertical deflection. The idea I had with Jean-François Klein, because we are two designers, Jean-François and myself, the idea immediately is to make a kind of hybrid system with suspension cables and with stay cables in the practically 1/3 of the span from the tower. Why is this solution efficient? It's just because the load from the train is directly taken from the place of the train to be driven to the top of the tower. And then, as we have very short spans, we shall speak of that later, this load on the top of the tower is driven back almost directly to the ground. So the tower doesn't deflect very much, and of course, the result is that the vertical deflections are divided by a factor which is about 3 to 4. This is completely different, and with this system, it is possible to have a suspension bridge with a streamlined box girder which can carry in the same time, at the same level, the train and the roadway. This idea is not new. We have not invented something new. This was done in the 19th century, for an example, by a very famous engineer, John Roebling, who was German but working in the States, as everybody knows, who made two bridges like this. The Niagara Bridge, which was built in wood, with the trains above and the carts, because they were not yet cars, it was carts with horses, at the lower level. And of course, he reproduced the idea with only a road bridge for the Brooklyn Bridge. In this bridge, the interest of having these stay cables in addition to the suspension was to make the bridge more rigid with a rather flexible deck. This idea was used by some other engineers, very rare, still in the 19th century, like on this very small bridge in France, the Saint-Marien Bridge. Using this concept made possible to have trains and cars and motorway at the same level with a streamlined box girder with the same type of shapes as for the first two bridges. Some ideas now. What we call the highly rigid bridge, because as it was written in the contract, suspension bridge, it was not really a pure suspension bridge, but it was a good bridge. And in the competition, this was a single solution with a streamlined box. All the other ones were with a big truss, which was rejected by the government, Turkish government. The span of the bridge is 1,408 meters. The competition document were with one tower in the Bósforo on the European side. But we immediately thought that it was not a good idea for many reasons, ship collision, works in the Bósforo and so on. And we decided to extend the span by about 130 meters just to avoid working in the sea and to save time. Because one of the big facts is that must tell a small story. In fact, I received a phone call for a friend of Astaldi, connected with this Turkish company, İçtaş, with whom these two companies had worked before in Turkey, in Russia. And Luigi Realini called me and told me, Michel, finally, with İçtaş, we decided to go for the competition for a concession of 150 kilometers of motorway, including a third Bósforo bridge. Are you ready to come with us? Yeah, of course. And with whom we can go, actually. We can go with Jean-François Klein and his design office. And then I asked, when do we must give the project? It was 26th of February. 6th of April, he told me. What? Fortunately, it has been a small extension. We could give the project on the 26th of April with the bid. And that is now exactly 4 years ago. And this week, the last segment will be lifted. This means that in 4 years, we passed from a white sheet to almost a closure, which is next week. This is something fantastic. The tower are 329 meters high, and this is the functional cross-section. You can see that the bridge is extremely wide, 58.5 meters. You know, the Champs-Élysées are about 70 meters. It's almost as wide as the Champs-Élysées in France. You immediately see that we installed the railways in the middle to avoid torsional deformation, and the one roadway on each side, and at the edges a sidewalk, but a sidewalk which is not for pedestrian, only for service and maintenance. This is the look of the bridge as it was designed in April 2012, and the same at night. Just to have an idea of the position of the bridge in the world construction, if you look to all bridges, this is the 9th in the span. There are several a bit longer. Of course, this is the bridge which has the longest stay cables in the world. And if you take the area of the suspended span, the length multiplied by the width, this is the bigger span in the world. And this is the longer span with a railway. I said we had practically 8 weeks to develop the design. In addition, for the fan, the first 2 weeks I was sailing in the Caribbean, and the last 2 weeks Jean-François was sailing in the Caribbean. So we had to rush very quickly. And the tower has been designed by Jean-François when I was sailing, and he decided for the elegance, for the architectural elegance of the bridge, to have slightly inclined legs. You will see that it has a very important result. As, of course, the main suspension cables and anchor have to be vertical for simplicity, this means that the main cables and the anchors have to be on both sides of the railway tracks, the roadways being cantilevering on both sides. This is, of course, reducing the torsional rigidity of the bridge, which is an important fact. A view of the bridge. Now, I pass very quickly because we could spend the whole day to discuss about this project. Some most important data. The most important one is the importance of live loads. First, because we have trains, and these trains are not light trains. This is heavy trains, 8 tons per meter. In addition, as there is some concern in Europe about the evolution of train loads, we have to factor for service limit states this weight of 8 tons per track by a factor of 1.33. And in addition to this, the Turkish code gives very heavy loads. They are even heavier than the Euro code, which is stupidly heavy. To give an idea, this importance of the live loads changes very much the design of the bridge, because the proportion of live loads compared to permanent loads is especially high for this bridge. If I took the example of the Normandy Bridge, the ratio of live loads to permanent loads is 0.28. If we look to the Bósforo Bridge, it's 0.54. This is almost double. And this has big impact. For an example, just for this example, this means that the sag of stay cables is very large, because under permanent loads, the tensile force in the cables is rather low, and we are of course limited by the code for the extreme load. So we have specific problems due to the load. This is the most important problem. It is much more important than earthquakes. Of course, everybody knows that Turkey is a very highly seismic country. But fortunately for us, and this I can show on this one, the main fault, which is the North Anatolian fault, is passing in the Izmit area and not in the Bosphorus, where the earthquakes are less important. When I say less, don't think it's small, because the peak response spectrum is 1G for the Bosphorus, but it is 2.5G for the Izmit area. So earthquake is not very critical, because in addition, we have a very long span bridge, meaning that we have long vibration periods which are much less sensible to earthquake. So earthquake is never a problem for our bridge. Wind, of course, is much more critical, but I will not discuss wind. We shall have a lecture just some minutes later on wind forces. But we had to make some records. We installed a temporary tower very close to the bridge to make correlation with meteorological station in order to have good data. And we have today 3 years of records locally. We made many tests in the CSTB and also at the Politecnico di Milano. CSTB made the climatic analysis and the small test, and the Politecnico made a very huge aeroelastic model with 3 configurations, the completed bridge and 2 erection configurations, including one which has finally not been used. Now, I must go on the design development. First, we must see which are the different parts of the bridge. We have the main span, logically, but you see the slopes on each side are very stiff, so that we have very short side spans. And so in fact, the side spans are not on the full length of the system. We have in fact side spans, we shall see in concrete, and the longer backstays are directly anchored in the ground in what we call the ground approaches. Initially, our first sketch was with a purely steel girder. Finally, to limit the cost, the side spans are in concrete, and only the main span is an orthotropic box girder, of course, to limit the weight as much as we could. What is also important is which are the conditions at support. Of course, we have vertical supports everywhere, at the tower, at the piers, at the abutment. We have transverse restraints only at the towers and the abutment, because the side spans are so short that it would have been a disaster to try to have transverse restraints on the piers. And we have no longitudinal restraints, because we refuse to concentrate the longitudinal seismic force, which could this time be a bit bigger, on one of the towers. So the bridge is completely free, longitudinal, like a pendulum. Now, we shall look how the suspension is organized. And this is very important to understand. First, we have the central part, which is the purely suspended section with the deck suspended by the hangers to the main suspension cables. Closer to the tower, on the contrary, we have the purely cable-stayed part of the bridge with 11 pairs of stay cables, to be more precise. And in the middle, we have what we call a transition zone. Why we need a transition zone? It's because, as I said, the cable stayed system is much more rigid than the suspension system. If we had passed brutally from cable stayed cantilever to a purely suspended system, then there would be differential deflection at the connection between the two, because in the central part it would have been very flexible. So the transition zone is designed to produce a progressive reduction of the rigidity to pass more softly to a very rigid system to a more flexible one. Now, going to the backstays, we have stay cables anchored in side spans, logically. This time, the stay cables are not anchored at the deck edges as in the main span, where we need to do that for the torsional rigidity, but they are this time anchored on both sides of the railway tracks because we have no anchors we could do there. And finally, we have a certain number of backstays which are directly anchored in the ground approaches. This has very important structural consequence. We have not the classical balance of a cable stayed bridge. Looking now, I first look at the 17 pairs of stay cables in main span balanced by 17 pairs in side span. The load in the main span, I just think of permanent loads because live loads, it works differently, and we shall see how it works. But for permanent loads, each segment weight is taken by a pair of stay cables driven to the head of the tower. And then, in such a way that the tower remains vertical, the horizontal component of the cable force is balanced by an equal component of the tensile force of the backstay, corresponding backstay. Of course, the tension is a bit bigger because the angle is bigger, but that's it. And then, of course, when I look to the effect on the deck, the horizontal projection of the tensile force in the main span is exactly the same as the horizontal component of the backstay in the side span, because we have selected the tension for this to balance the forces in the tower. We have a perfect balance. Fantastic. But this is not the case when we look at the 5 longer cables. These 5 longer cables take the load, drive the load to the head of the tower, but then they are balanced by cables which are anchored to the ground. And so the horizontal component of the tensile force in the main span cannot be balanced by horizontal force in the side span. Where this force is passing? It passes in a tensile force in the central part of the main span. This bridge has a tensile force of 8,000 tons under permanent loads in the main span. Well, of course, after that, the system is very clear for suspension. This is classical. The forces, the loads are taken from the deck to the hangers, from there to the suspension cables, and driven to the Anchorage Block. This part is classical. Now, looking to what happens when a train is passing. Once again, the fact that we have backstays anchored in the ground is creating a problem. If I look to that, the loads of the train, which are taken by the 17 pairs of cables which are balanced by 17 backstays, are more or less equilibrated, and so this is okay. But the 5 pairs of cables which are not balanced by cables anchored in side span but in ground approaches cannot be balanced. This means that we have a resulting force which is moving the deck towards the abutment. And the displacement is rather large. If we had not done anything, this movement produced by the passage of trains at quarter span would have produced a longitudinal displacement so high that the longer backstays anchored in side span would have been very much detention. It was too much. We had to limit this effect. This effect will be limited by 3 factors. One, this is of course the elastic reaction of stay cables, because when the deck is moving backwards, you increase the tension in backstays, you decrease the tension in the front stays, of course, and the same on the other side. So this is the first action. And then I decided to use what we call pendular bearings. I shall show in a minute how they work. They turn, and by turning, they produce a reaction. And in fact, the pendular bearings introduce 2 effects: one elastic reaction by the curvature and friction, so that globally, the train, the longitudinal displacement produced by the passenger train is limited by the elastic reaction of the cables, by the elastic curvature effect of pendular bearings, and by friction. This is this is a pendular bearing. You see it's a very big element, which is perhaps, I don't remember exactly the weight, it's 30 or 40 metric tons. We shall see which is the dimension. In this one, this is a pendular bearing for the tower with a radius of curvature of 2 meters. I will not make the demonstration of the way it works, but if the deck is going backwards, the rotation element turns in the opposite direction, and we can connect directly the rotation to the displacement by this formula, and in the same time there is a small vertical movement produced by the displacement. This is the selection of the radius of curvature. Of course, it was useful to have rather small radii of curvature to produce an important reaction to limit the train movements. But of course, at the abutment, we have a classical bearing because we cannot afford having a vertical movement. And of course, we had to make a progressive increase of the radius of curvature so that we don't produce a brutal vertical displacement of the deck. It was necessary to make tests. It has been done in the Euro Center in Pavia, in Italy, by a section of the effective bearing. This is at scale, but of course we have not the full width of the bearing. It's 1/8 only, and to make tests to show, to measure the friction coefficient and to evidence the behavior of this system. Now, we shall look at the consequences of this design, which is very specific, on erection sequences. We start very classically by erecting concrete side span on scaffoldings. You will see photographs later, clear. Then we shall erect the cantilevers with steel segments, which are 24 meters long, and each segment, you will see that later, the weight of each segment is 950 tons. It's not a small weight, it's very big. And until cable number 17, the series of cable balanced by backstays, construction is classical. Honestly, we produce a connection at the abutment to be able to, with press-dressing tendon and concrete blocks, because we have to take the possible forces if there is an earthquake and wind. But it is absolutely classical. But then it stops to be classical when we complete the cantilever. Normally, we had to complete the cantilever until the pair of stay cable 22. Practically, for other reasons, I don't enter in that. We have been only up to 20 for things which are very, very detailed. But at this time, the horizontal force, the horizontal action of this cable has to be taken something. It is passing at the abutment. After that, we shall erect the main span, classically for suspension bridges. It's not so simple because as we have a very rigid element a very rigid cantilever which is cable stayed. Attaching the new segments is not easy because when we start the erection of the fully suspended segment, the main stay cables are 15 or 20 meters above their final level. And so, of course, we have to take very specific measures to solve the problem. But as regards global forces, there is nothing new. We still have the effect of this unbalance of the stay cables, which are not balanced by backstays. So when we make the closure, which will be next week, how can we make this? We shall push, one side will be fixed, we shall push the other one with jacks at the end, with a force which will be something like 6,000 tons, to push the cantilever to be joined to the other one and to attach it with temporary elements, and then we shall release the jacks. And at this moment, the force which was at the abutment on the jacks, and first in the concrete block and then the jack, will pass in tensile force in the main span. See, it's a very complicated system, but it is a consequence of the fact that we had so short side spans. Now we go to some recollection of data. I don't enter in geotechniques because it's not very specifically interesting and I'm not a specialist at all, just to show what is the foundation of this bridge. Each tower leg is supported by what I call a well. It's a pile, but a pile which is 20 meters in diameter and 20 meters deep. There's big concrete blocks, as you can see. In fact, initially, we suppose it would be a cylinder filled with gravel. Finally, it has been the Turkish who made directly this work, considered easier to make it full concrete. It's massive concrete, of course, with reinforcement. You can see here the European bank with the two excavations which were made in the first month of 2013, and some views of inside. You know, it was working. We had not 1 liter of water coming. You see, the decision to make the span a bit bigger to avoid working in the sea has been fantastic. It has been a great help. And to give an example, we started the erection of the Bósforo bridge 1 or 2 years after the beginning of the erection of the Izmit Bay Bridge, and we will finish before because we had not to make offshore works. Now, a view of the Anchorage Block, which is almost classical. The single fact which is not classical is that since we have this stay cable system, the size of the cable is much smaller than for a purely suspended bridge. You see the Anchorage Block is in the back of this slide very clearly. The cables, as you will see, will be anchored in the middle, but of course it is much wider in order to produce the weight what you need. We had some bad surprise on the Asian bank. As you see, this green part here is a fort. Between two parts of rocks, we had some clay. And this is the other side in Europe, which has been much better. You see the importance of reinforcement. You see also, this is the central part of the system. You can see also the places where we shall anchor a bit later the cables. Now, construction has progressed very much, and you can see very clearly what you see here. This is the places for the press-stressing tendons, which will drive the tensile forces at the bottom of the Anchorage Block, and we shall have a special device that you will see later to attach the different cable elements to these anchorages. Another view at the same time, but you have not all the concrete blocks there. We pass to side spans. Of course, you see that... You see that as we have these cables which are anchored with 5 pairs of cable anchored in the ground approaches, of course, there is a longitudinal force going towards the Bósforo. So we had to put what I could say shear case, that's big concrete shear case in the rock to balanced with longitudinal forces. And the system with just, in fact, we have just a big concrete block with 2 tunnels to anchor easily the stay cable inside. Some views of the system. You see the 2 tunnels there of the ground point in which the cables will be anchored, these 5 pairs of cables. You see one getting out. Of course, as in all this construction, what is very important is the geometric accuracy of the positioning of all these tubes. Concrete side spans, we have 1 abutment and 4 piers. In fact, you see, we have been obliged already to excavate the ground to put these side spans. The slopes are so stiff. A 3D view, you can see, of course, that we have preferred to have many webs, better than transverse cross beams. It is much cheaper, in fact. You can see also the stay cables, which are anchored on both sides of the railway track, and the dampers, the very big dampers. I have not the time to speak of dampers, but it's clear that due to the fact that we have very high live loads and we have a very high sag variation, we have low tension under permanent loads, the stay cables are much more sensible to cable vibration than usually, so we had to introduce more damping than usual. The scaffolding to erect the side spans and some views of this erection progressively. And I pass to the tower. The tower is a bit complicated due to the very good decision of Jean-François to put this shape. And we have just on top a kind of steel bracing between the 2 legs. The shape is more or less triangular of the legs, but the dimensions are all changing, but in such a way that it can be done with an industrial moving form. And of course, we need, sorry, I made a mistake. We need, of course, many struts to take the effect of the inclination of the leg during construction. I pass on that, which is a pure computation problem. Forget it. Now, construction. I start with something I didn't like at all. Against our strong opinion, the contractor. The contractor is a joint venture of Hyundai and SK, 2 Korean companies, because the concessionnaire, Astaldi and Ichtas, ICA, it means Ichtas Astaldi, the concessionnaire with the 150 kilometers of motorway realized that he could not do everything. So he preferred subcontracting the bridge to a Korean consortium of Hyundai and SK. And against our opinion, everybody, the contractor and the concessionaire, decided to cast the tower legs with slip forming. Don't do that, especially when you have a big tower like this. When you want a good quality, avoid slip forming. It has been, they thought it would be quicker. It has taken more time because there have been many problems. The slip form was deformed. Forget that. So the slip form were used up to 208 meters. And then, you will see why in a minute, we passed to what would have been the good solution from start. It's the self-climbing formworks. This is what you must use, and you must call for a good one. There are very good companies able to do that in the world. Personally, I have much experience with Perry, but there are other ones, and it works very well. So why it was absolutely mandatory to change, because with the slip form it would have been a nightmare, it's because the stay cables are anchored in steel anchorage elements, because this is the good method to anchor cables. Because, you see, your front stay has tension on one side, and the horizontal part has to pass on the other side. And then you have a tensile force in the middle. To try passing this tensile force in concrete, forget it. The good thing, as the idea came from a Belgian design office, Grèche, that I reused it for the Normandy Bridge, and in all my bridges now, stay cables are anchored in steel boxes in the towers. It's a bit complicated. Just look this complex shape, because here with the stay cables anchored on the edges main span, in the middle and side span, it's a bit complicated. Fabrication was not bad at all in a local factory. And just look the scale of the first one. You see the truck there? The truck is here. And look the size of the first anchorage element. It was so large that we had to take it in two parts. This is always the problem for the cables that are enclosed closer to the pylon, which are passing on 20, 30 meters in the concrete because they are so vertical. So that worked very well, finally. The view in winter, towers are progressing quickly. And now we see what is the top of the tower. It was in November 2014. And this is the place where later the deviation saddles of the main suspension cables will come. Now, passing to the steel deck. I will pass very quickly. This is a steel orthotopic box girder, as you see, with steel stiffened plates. There is nothing special to say, except that, of course, we need a very high quality of welding. We need robots to make things properly, because if you try to make this with ordinary means, it's hopeless. A 3D view. And now we can see the first segment coming on a barge. This was our Christmas gift in December 25th, 2014. As we had been obliged to make a kind of jetty, in an embankment in the sea, the first elements had to be brought by the barge, put on a crawler, moved to the tower, and then lifted with the derrick from the tower. I remind that each of these segments weighs 950 tons. And of course, the derrick itself is not a little element, it's 350 tons each, because there are two elements. You can see the erection, and of course, there has been a big fight to know if the segments will be welded or bolted, and we won finally, it is welded. Some views, there is nothing to explain very clearly. Views at night. A new segment has been lifted. Now it is taken by the derrick, and we are, after some geometrical adjustment, the welds are made. The cycle is 9 days to weld, from the finishing one segment to finishing the next one. It's 9 days, including lifting, adjusting, welding, and tensioning stay cables. We are almost at the last stay cables. Here we are probably at 18 or 19. And the last view. We pass now to the main cable. The main cable is made of a series of what is called strand, which is not a strand. This is just a bunch of 127 wires of 5.4 millimeters each. And we have 113 of these so-called strands in the main span. And as the back cable is more inclined, we need more. We pass from 113 to 122 for each. So we have 9 strands of 127 wires anchored on the saddles. A view of the saddle, of course, the upper part of the towers is pure decoration. And now the saddles, in fact, each saddle has been made of 2 elements, because it would not have been possible to take the saddle in one single piece, because it would have been more than 200 tons, and it was not possible. And these saddles have been cast in Italy. I don't remember just now the name of the company, but it has been a very good work. You see the channel in which the cable will pass. The diameter of the cable is about 80 centimeters. And now we start installing the cable. And for this, we need what is called a catwalk. The catwalk is that. This kind of very light pedestrian bridge, which is spanning from the Anchorage Block, passing to the top of the tower, going into. Personally, I don't like very much walking there. And the cables are coming, the elements of 127 strands are stuck on one bank, and they are with a tensile rope, they come, and on the catwalk, you can see on the left here, the one is coming. In fact, they are coming two in the same time, and we have to pass this element on top of the saddles. You can see the element which is tracting the cable there, and there is on the side you see a kind of wheel which is just the counterweight, because you can take only on one side, of course, and we pass like this on top of the saddle to place the cable exactly at this position. Of course, there is some elements to make a classification of these different elements to pass them in the saddle, which is not so simple, in fact, because it's more or less stable. You see the new cable, you see the socket here, which will pass by a system of wheels on top of the saddle to take its position. And then, after that, it goes down to the Anchorage Block, which is at the bottom here, of course with a new classification, and you can see this cable with its socket going back to be attached at the bottom to a system of press-tracing bars which drives the force from the socket to the Anchorage Block with the press-tracing tendons, which themselves drives the force down to the Anchorage Block. Now you see the progression of construction. Now all the wires have been installed, and you see they came with an hexagonal shape, and from this hexagonal shape we are to produce a circular shape by a kind of compression system of the cable with a system of jacks which make the cable perfectly circular. That's done. Now we can install the cable bonds, which have been also cast in Italy by the same company. One of these cables was installed with many discussions about fractal mechanics and so on, so on, so on, so on. And now on top of the cables, the Koreans have installed a big machine with heavy lifting jacks, because they're strand jacks, which will be used to lift the segment from barges. And you can see now, finishing of the erection, with, you see, the two elements rolling on the main cables, and with their strand jacks, they lift each new segment from a barge. You see? We try to make it symmetrically to avoid big displacement of the cable, of course. So as soon as we can, we have two segments lifted in the same time. And then, as before, they are adjusted with the hangers. We have the first hangers are temporary hangers because, of course, we have this problem of the level of the main suspension cables. But after 3 segments, we use directly the final hangers at their final length. You see? And you see in the same time here what's something which is important. This is the protection element to weld. One of the big advantages of this solution. It's clear. We save time with this concept of cable stay and suspension. Because, you see, we could erect all the cantilever with the stay cables during the same time as we were installing the cables, the main suspension cables. And so we save time, and this is one of the reasons why it has been built so quickly. And in addition, when we have to install the suspended segment, the main part, as we have no important forces already in the cantilever part, we can have welds on several segments at the same time, and so we have a much shorter cycle than for the cantilever. This is a view now of about 2 months ago. Some beautiful views. This one is much shorter. I've not more recent photographs. I just said that tomorrow, normally, they will lift the last segment, which is a short one, which is a segment which will make the connection between the two cantilevers. And next week, we shall push with the jacks one side to meet the other. That means that in exactly 4 years and 1 or 2 weeks, we pass from the white sheet to what will be in July or August, this fantastic bridge, the third bridge on the Bósforo. Thank you very much for your attention.
Thank you.